Have you ever wondered if there are any rules the universe actually follows? No exceptions? I'm not talking about suggestions. I mean ironclad, unbreakable laws. Well, it turns out there are. And today, we're going to dive into the really beautiful reason why they even exist.
All right, welcome to the deep dive. Today, we're exploring the big ones, the fundamental conservation laws of physics. We're talking energy, momentum, and electric charge. These are the absolute bedrock rules that run the show, from something as simple as throwing a ball all the way up to colliding galaxies.
And I love this quote because it really just nails it. These are the rules of the universe that politely remind us we can't get something for nothing, no matter how much coffee we drink. It's so true, right? You can think of these laws as nature's ultimate accounting system. You can move stuff around, you can change it, transform it, but you can absolutely never cheat that final tally. Yeah, that's the bottom line. Energy doesn't just vanish, momentum doesn't just quit, and electric charge, it keeps the whole world buzzing. And I mean that literally. At their core, these laws are what give our universe its consistency. They're the reason it's predictable and not just some chaotic mess where things can just pop in and out of existence. So let's get into what they actually are. All right, let's dive into physics' 3 big rules, the real VIPs of the physical world. So here they are, the big 3. The conservation of energy, the conservation of momentum, and the conservation of electric charge. Let's break them down one by one. Okay, first up, the big one, energy. You've probably heard this a million times, right? Energy can't be created or destroyed. It only changes form. A car engine is a perfect example. You've got all this chemical energy locked up in the fuel. When it burns, that energy turns into the car's kinetic energy, its motion, plus a whole lot of heat and sound. But here's the kicker. If you could somehow capture and measure all of it, the total amount would be exactly what you started with. No more, no less. Next up, we've got momentum. The easiest way to think about this is just oomph, or quantity of motion. It's simply an object's mass times its velocity. And the classic example here is a game of pool. When the cue ball just smacks into the rack, it might look like it stops dead in its tracks, but its momentum didn't just disappear. Nope, it got transferred to all the other balls, sending them flying. If you added up the momentum of every single ball right after the break, it would be the exact same as the momentum of that one cue ball right before it hit. And last but not least, electric charge. It's simple, really. The universe's total electric charge is always constant. You can definitely move charges around. Think about a chemical reaction where a little electron jumps from one molecule to another, but you can't just create a negative charge out of thin air. For every new negative charge that pops up, a positive one has to appear somewhere else to, balance the books. Okay, so for a really long time, physicists just took these laws as facts. They were never, ever broken, so that's just how the universe works, right? But come on, that's not a very satisfying answer, is it? You can't help but ask why. Why these 3 things in particular? Why does nature care so much about conserving energy, momentum, and charge? Well, it turns out there's a profound reason. And the answer, the really beautiful why behind all of this, comes down to something called symmetry. But hold on, it's probably not the kind of symmetry you're picturing right now. You see, when we hear symmetry, we usually think of something visual, right? Like a butterfly's wings or a snowflake. You rotate the snowflake and it looks exactly the same. But in physics, symmetry is a much, much deeper concept. It means a law of nature, a fundamental rule, stays exactly the same even when you change something. We're talking about an invariance. Basically, symmetry in physics means the rules of the universe just don't care when you are or where you are. Think about it. The law of gravity worked the same way yesterday as it does today. That's a symmetry across time. And it works the same here on Earth as it does way out in the Andromeda galaxy. That's a symmetry across space. So the big question is, what in the world does this have to do with our conservation laws? Well, that incredible connection was discovered by one of the absolute giants of 20th century mathematics, Noether. Back around 1918, she came up with this idea, this theorem, that was so profound it completely changed the game. And this is it. Noether's theorem. Honestly, it's one of the most elegant and powerful ideas in all of science. What it says is this: for every continuous symmetry you can find in the laws of physics, there is a corresponding quantity that must be conserved. It's not a maybe, it's not a coincidence, it is a direct mathematical consequence. This is the aha moment. This is the great connection. So the fact that the laws of physics don't change over time, that symmetry directly leads to the conservation of energy. The fact that the laws are the same no matter where you are in space, that symmetry is why momentum is conserved.
And then there's a slightly more abstract one called gauge symmetry, which we'll talk about in a sec. And that is why electric charge is conserved. It all connects.
So to really let this sink in, let's flip the script. Let's ask, what if the universe wasn't symmetrical? What if the rules actually did change? Yeah, what if time wasn't symmetrical? Just imagine a universe where the basic laws of physics were different on Tuesdays than they were on Fridays. Well, if the rules changed over time, you'd get these special moments where, hey, maybe the rule about energy is off for a minute. And in that moment, energy could just appear out of nowhere or just vanish. But that never happens. Because the rules are always the same, there are no special moments. The universe has no favorite time to create or destroy energy. And so, energy has to be conserved. Okay, same idea, but for space. What if the laws of physics were different depending on your location? That would mean there are special places in the universe. Imagine a boat just sitting still in the water. If it drifted a few feet to the left into one of these special spots, it could suddenly just start moving, poof, gaining momentum from absolutely nothing. Since we don't see boats doing that, we know the rules are the same everywhere. And that's why momentum is conserved. Okay, that brings us to our last and admittedly most abstract one, gauge symmetry. But stick with me, there's a really good analogy for it. Think about your height. Your actual physical height is what it is, right? It's a fact. But if I measure it from the floor, I get one number. If I measure it from sea level, I get a totally different number. Did your height change? Of course not. All that changed was my 0 point, my reference. Well, in electricity, there's a similar idea with something called electric potential. You have total freedom to set the zero for that potential wherever you want. And no matter what you choose, the actual physics, how charges push and pull on each other, doesn't change one bit. That freedom, that fact that reality doesn't care about your 0 point, is gauge symmetry. And just like before, Noether's theorem kicks in and says, because that symmetry exists, electric charge has to be conserved. It's just beautiful. So you see, these unbreakable laws aren't just arbitrary rules the universe decided on. They are deep, direct consequences of the fundamental symmetries of our universe. It's incredible. And look, unlike your high school physics class, we promise to keep things lively around here. So why not subscribe to the Deep Dive? It's literally the one place where conserving energy means you get smarter without even lifting a finger. And speaking of conservation miracles, I have to give a shout out to our producer, FireflyHaku, who somehow organizes all of this, balances the chaos, and still manages to shine bright. It's proof that even in physics, brilliance always finds a way. All right, that's it for this one. Thanks so much for hanging out. If you enjoyed it, share the love and come back for round 2.